She received her PhD in 2006 from Jadavpur University in India and worked as a postdoc at the Abu Academy University, University of Turku, and in Aalto University as Academy of Field and Research Fellow. She also worked at MIT and in Max Planck Institute. And her current research focus on CMOS and flexible substrate compatible heterostructures for neuromorphic computing and adaptive his talk is neuromorphic computing and adaptive sensing. So please, the floor is yours.
Thank you very much.
Yes, please.
Okay. So first of all, thank you very much to the organizers for this invitation. Clivia, it's really an honor to be here and addressing all of you. Last 2.5 years have been really different. We all have been just talking over, email and internet and other things, but always talking face to face and discussing things means a lot. Yes. So.
That's the laser. Should be able to move backwards.
Okay, it worked. Yes. No, it's fine. It's fine. So, yes, I mean, although the title of my talk is quite broad, like neuromorphic computing and adaptive sensing, they are at the very, heart of all different activities going on in this field, but it's really a broad field again, and I can only show you some results from my research and some ongoing other activities that will probably give you some idea on the ongoing activities which are leading more towards the next breakthrough in these fields. So yeah, this is briefly my research career. I started from the city of Calcutta. I am from India, from Calcutta, and after my PhD, I moved to Finland in Abu Academy University in Turku, and I started working in spintronics again. Also at that time, it was a very happening research field, and I moved to MIT for some time also to work in Francis Bitter Magnet Laboratory using the magnetic tunnel junctions and other things. But then I moved to Finland again, but this time to Helsinki at the Aalto University, where I started working on ferroelectric materials mostly, and also in Max Planck, I worked on ferroelectric polymers quite a lot. And currently also my research is focused on ferroelectric based memory development for neuromorphic computing and adaptive sensing. So a little bit about the VTT Technical Research Center of Finland. For the last 3 years, I have been working in VTT. VTT's research activities are more, you can say, at the interface of basic research and industrial development. So we work on different technologies, starting from technologies which are in exploratory phase to more technology which are ready for industry, or even completely industry focused technologies. So there are different VTT activities going on in different fields. I mean, starting from biotechnology, food research, nuclear safety research, and metrology. Different technologies are researched in VTT, but we are part of this Micronova. This is our workplace. You can say it's close to Helsinki region. We have the largest clean room in the Nordic countries, so very big research facilities here. And we work on mostly micro nano electronics and quantum technologies. Some of the major technologies that has, activities in Micronova is this silicon photonics and integration, active silicon devices, MEMS, RF components, superconducting devices, and 2D materials based devices and integration. And very recently, VTT got its first quantum computer. So we have a 5-qubit operating quantum computer now in Micronova, and we are also with neuromorphic computing as well. We are trying to work in collaboration with quantum error correction kind of applications. So related to the sensing and memory device and their integration, which is my research topic, we have several different research infrastructure ready for the device fabrication and characterization. So mostly things that we work on with these nanofab processes are, 2 e-beam lithography and of course photolithography and laser writer lithography and different CVD, ALD, and physical vapor deposition systems, and annealing and wafer bonding, and different structural and electrical characterization systems and integration. So with that, I'm starting with my presentations brief outline that I can start talking about the major challenges with the traditional computing hardware, especially dealing with AI tasks, which are really data intensive, and the CMOS computing system is not being very useful there. And starting from there, why in-memory computing is needed, what is the state of the art in the novel memory technologies, why in-sensor or near-sensor computing is important, and then how ferroelectric tunnel junctions and field effect transistor-based devices can contribute to different systems. And I finally give you some brief overview from device to systems level performance and benchmarking. And finally, I'll conclude. So as it is now very much known to everyone, one of the big bottleneck is the von Neumann architecture, which is extremely efficient in precision computing. But when it becomes data intensive tasks, it cannot handle huge amount of data transfer, mainly because of the reason of physical separation of memory and the processor unit. So each time we run any AI model on the normal computer, it keeps on doing data shuttling huge number of times between the memory and processor unit. And most of the time, the processor just sits there idly waiting for data to arrive from the memory. And it's not only time consuming, it's at the same time very energy inefficient. And in last few years, probably there were several reports like running a complex AI model on the normal computer. It costs, gigawatts of power, almost like running a whole thermal power system only to run one AI model. And the cost of carbon footprint is huge, like one AI model running on it is probably a lifetime of 5 cars total carbon footprint, something like that. So this is totally unsustainable to do all the AI tasks. So it's almost inevitable that people have to move to a different kind of architecture and computing paradigm to avoid this. So beyond von Neumann architecture is one of that solution. And the idea here is to learn and adapt ideas from biological information processing, which is not very precise computing, but at the same time, it is good enough. And it is extremely efficient in doing unstructured data handling. So large scale of unstructured data, that is the thing that AI always have to handle, and all the internet connected devices and everything, they always need to handle a huge amount of unstructured data, and their biological data processing is one key solution that is very important. See there. So how in-memory computing works? It's basically utilizing the analog resistive switching property of devices. So memory resistors or memristors come into play here. And normally this kind of an architecture is used where you have a crossbar, and at each cross point you have a memory resistor. It has a certain conductance value, and there are some mixed signal interface on the crossbar, but the computing takes place in this analog crossbar. And when you have a voltage input through this line, and when you take the current output along the perpendicular line, it basically applying the Ohm's law and Kirchhoff's current law gives you the conductance of, which is a vector matrix multiplication and summation using the entire thing. So it gives you the multiply and accumulate operation from each crossbar, and conductance of each memristor and the voltage input to that line, they are basically gives you the current output here. And that's why it's a very highly parallel operation where the computing basically takes place inside the memory resistor or the memristor. So that's the in-memory computing thing, which is a very parallel operation. And that's why energy and time efficient. And one of the main problem of this kind of computation or in-memory computing is that we depend quite a lot on the analog conductance states of the memories. And from physics perspective, you always know, like, on and off states of any device is much easier to control compared to the intermediate states, because there are always issues in exactly having some intermediate states and repeatably, like 10 to the power 5 cycles, 10 to the power 6 cycles. You always want to apply a certain voltage pulse and want to get exactly same current output from the device. And that's not very easy. So this remained one of the key challenges, like irreproducibility of the intermediate states. Then one of the key technologies that you know about, mostly you hear about, are the RRAM technologies, where mostly devices are oxide filamentary based memories. And in those memories, one key challenge is a large leakage current. So when you are accessing one device, you basically are kind of disrupting the neighboring devices as well, because there are always some voltage drop across those devices. So if the leakage current is high, the crosstalk between devices becomes quite a significant issue. And then you are not only, what you are expecting to get from one is not exactly what you are really getting, because the neighboring devices also give you some signals which you don't really want. So that makes a larger array level implementation a difficulty. And another thing is, if you have a large array, the voltage drop across these lines when it's in nanometer scale is not something that you can ignore, and that makes the device switching currents and everything different. So there are kind of issues that needs to be solved before the in-memory computing becomes really possible in all cases that we want them to. And currently, the memory landscape is something like this, which was very nicely put into in this article, where we have shown like all our CMOS memory, starting from static random access memory, dynamic random access memory, and flash drives, and all these kind of devices, and what was their plus point, minus points, and all these issues were very nicely covered in this article. And currently, all the neuromorphic computing architectures are basically dealing with either spin-based memories or phase change memories, or this oxide RRAM, where this oxygen ion filament formation and rupture is one key conducting element, conducting phenomenon, and also the metal bridge conducting bridge RAM, where actually one of the electrodes are the more active ones. So under electric field, those electrodes move inside the insulating layer and form that conducting bridge and rupture. But in both these cases, the major challenge being controlling the filament formation and its geometry, because that basically makes your intermediate states more stable. And that is one of the key things in analog computing systems. So forming free operation is one key criteria for then the reproducibility of the devices. And phase change materials are in general much, easier to handle in that sense, because it has no really filament formation there. But because phase change materials work on the principle of formation of crystalline phase and amorphous phase under electric field, the state, this crystalline phase over time is not very stable, and the retention of your programmed state, that's why it becomes drifting with time. So there are issues actually with most of these technologies. And from ferroelectric technologies, this ferroelectric RAM is actually a more mature technology, where you basically have one transistor and one capacitor kind of architecture. And this is already a technology that is in market, so it's a really more matured one. But the ferroelectric field effect transistors and ferroelectric tunnel junctions are the more emerging ones, where you have the possibility of doing much low voltage operation. And okay, in ferroelectric RAM as well, it's non-destructive, it's not non-destructive. So each time you read out the state, you basically destroy it. So you have to reprogram the device over and over again. And that's not very suitable for the purpose. So that's why the idea for the ferroelectric field effect transistor and the ferroelectric tunnel junction is here you have non-destructive readout. So you can read the programmed state with a smaller voltage, so that it doesn't change the ferroelectric polarization during the readout. And once programmed, you can read it as many times as you want. That is one key idea. And here mainly it's a normal field effect transistor, but instead of a dielectric gate material, you use a ferroelectric material, and the polarization you can control with an applied voltage. And ferroelectric technology is better from all the other in a sense that it's a voltage controlled technology. So there is no current controlling, and that's why it's the most power efficient solution for the current memory landscape. So, but the challenges are something like ferroelectric field effect transistors, what the current technology like CMOS technology platforms can offer you, and the field needed really to switch the ferroelectric polarization if it matches well, and if within the power supplied from the 180 nanometer CMOS technology or something is enough for the polarization to switch, and within very fast time scale. That is one important consideration, and I will come to that later. So this is actually from the recent article which I was working on the back end, CMOS compatible and flexible ferroelectric memories. And if we kind of compare all the CMOS memories and the emerging resistive memories, it's huge lot of parameters, of course, that anybody would like to have in order to say, okay, this memory technology is really suitable for this purpose. And it can be very safely said there is actually no memory technologies yet which can satisfy all the requirements that needed for different applications for deep neural network training or inference or spiking neural network applications. So based on the requirement, really, we need to understand and figure out what would be the most suitable technology that we need. So for in-memory computing, there was this, again, very nice article from Strukov's group, which showed that, okay, these are the main criteria that, that people consider, like reproducibility, endurance, reciprocal switching energy, speed, retention, on-off ratio, off-state resistance, so that in the when device is not doing anything, it's not eating up a lot of power. Then the current voltage, linearity, number of available state between on and off, these are all very critical parameters. And when we come to CMOS integration of those elements, there are other very critical issues as well, like the material that we are considering, not only if that is CMOS compatible, but if the process, if that is CMOS compatible, if the device will switch to all the on and off and intermediate states when we are considering the 180 nanometer CMOS technology, or even lower, if the voltage supplied by the CMOS transistors would be enough to switch those devices, then how fault tolerant the devices are, how noise sensitive they are, and the temperature window they can operate on. Also, if it has compatibility with other materials on the chip, they are all very critical points for consideration. So when I'm talking about this ferroelectric tunnel junction devices, they are basically an ultra thin layer of ferroelectric. As you know, all the ferroelectric materials are basically insulators. So through ferroelectric, we can only make tunneling currents to pass through one electrode to the other. So when we have two different metals, the barrier profile is asymmetric. And when the polarization switches from up to down or down to up, basically the charge carriers either accumulate or deplete at the interface between metal and ferroelectric. And that changes the tunneling barrier height for the electrons, and that gives rise to the on-off state. And this is the figure of merit, like tunneling electroresistance. For neuromorphic computing, it's not required to have extremely high on-off, but at least on-off ratio of 100 is preferred. So that intermediate states are not overlapping or very easily, drifting and making one state undistinguishable from other states. So that is one important consideration. And then the two different metal electrodes should have different charge screening lengths as well. But this charge screening length actually is very important for the retention of the programmed state, because if the bound polarization charge is not properly screened in the metal electrodes, then the polarization is not stable and it decays over time. And that means you will lose your programmed state pretty easily. So we have actually worked with various different kind of ferroelectric materials for these ferroelectric tunnel junction purposes. So mostly barium titanate and PZT is the stable standard material, but these are definitely not CMOS compatible. So, although you can get nice resistive switching from them and very reproducible, fast operation and everything, but for the current purpose, I won't go into very much great details of these results, because they will not serve the purpose for the CMOS back end of line processing. However, it was very interesting actually to observe, what I was telling you, that, okay, when we have two different metal electrodes, then the on-off switching ratio is high. But in this case, what we tried actually, both was LSMO electrode. So it was similar bottom and top electrode, but still we had very good on-off resistive switching ratio. And the result was seen from the TEM results, that actually, although the metals or the metallic electrodes are similar materials, but the interface effect is actually everything. So when barium titanate or PZT is grown on LSMO or LSMO grown on PZT, the interfaces are absolutely different. And those, change in out of plane lattice parameters and spacings was already enough to give those barrier potential asymmetry in those tunnel junctions. And here it's a polymer ferroelectric based device that I am now talking about. But although this is a polymer based ferroelectric, for any polycrystalline ferroelectric material, we have seen kind of similar properties from them, like hafnium zirconium oxide and others. So these devices had one metal electrode and one semiconducting electrode. And what that gives rise to you, when the polarization is switched from top to bottom or bottom to top, when the polarization direction is away from the semiconductor electrode, you basically form one Schottky barrier at the interface. And that gives rise to not only change in tunneling barrier height, but tunneling barrier width as well. And that change in tunnel barrier height and width together gives a very large on-off switching ratio and very controllable on-off, intermediate states, which is very promising. And with piezo force microscope, we could see that when you apply a higher voltage or a smaller voltage, you can see those mixture of the bright and dark domains. So it's possible that you land up in a mixed domain phase and you can control those intermediate resistance states. And we have studied many of those states, even though it's a semiconductor electrode with less charge carrier density, at least for several hours, those programmed states are very stable. So you don't need to reprogram them every now and then. So that was very interesting, but not only for the on and off state, and different conductance states actually needs to be not only very stable for a long time, maybe that's not needed, but for training of the devices with any algorithm, you basically need to know their long-term potentiation and short-term potentiation and depression behavior, so that you can program them accordingly. So by long-term potentiation, it means when you excite the device to a certain state with a set of pulses, and then if the conductance states remain to the excited state or close to that. And these time constants are actually very important when you are training your network. So they are, based on how you are exciting your ferroelectric domains, these also can change, like magnitude of the voltage pulse, duration of the pulse, and interval between pulses. All of them can actually affect your potentiation and depression time constants. So these are very important and interesting parameters. And for spiking network, actually one learning rule is spike timing dependent plasticity. So in a biological synapse, actually we get two directions, like the presynaptic neuron and the postsynaptic neuron. They both send signals to the synapses, and based on the overlapping of the two signals, our synaptic weight actually changes. And how they change, how symmetric they are, and all these things, they determine our learning ability. So the Hebbian learning, or anti-Hebbian learning as we call them. So these are kind of parameters that we need to find out from any devices, like how much when the pre-spikes and post-spikes overlap onto each other, how we can control the synaptic plasticity with those numbers. And for the ferroelectric tunnel junctions, we actually saw that even with nanosecond, 20 nanosecond pulse time, we could achieve all those plasticity mechanisms, and also spike timing dependent plasticity and everything. Although in this case, the depression threshold and potentiation threshold voltage increased, because it's 20 nanosecond pulse, and it always requires a higher amplitude to turn the device on and off. But with this pulses, if we estimate, devices actually can switch faster. It's just the instrumental limitation that we couldn't measure anything beyond 20 nanosecond, but we can do it faster, but again, at the cost of a bit increasing amplitude of the voltage. And the potentiation energy was of the range of picojoule, and depression energy was at the range of 100 femtojoules, which was close to the biological ones, but not exactly. So there are always options for improvement. And another interesting thing was when we changed the charge carrier density in the semiconductor bottom electrode, it's possible to change the time period of the ferroelectric polarization retention, because as I was telling you, the charge screening at the ferroelectric interface was really important. So the domain dynamics, how they are polarized and depolarized, depends on how much screening carrier density at the semiconductor interface we are having. And that's why when we have different doping concentration of niobium in the niobium doped STO electrode, you can basically see from very long-term retention, we are actually moving towards more short-term retention. And using that property, it's possible not only to get synaptic elements from the ferroelectric tunnel junctions, but at the same time, neurons as well. So the leak, integrate, and fire kind of neurons, which normally is implemented using several of CMOS transistors, which is quite a bit area consuming and power consuming as well, using a single memristor or memristor and capacitor and resistor network, so that you get the exact time period you want from your firing neurons. It's possible that only memristive based neuron circuit is also possible. So when we excite them with sub-threshold pulses, like I mean, you probably saw from the other ones that it's close to 1 volt is the threshold voltage for these devices. But if you excite them with 0.7 volts or 0.8 volt kind of voltage, you see an oscillatory pattern of the output current. And here, when you change the voltage, amplitude, or frequency, you can integrate a few of these pulses for some time, and then you suddenly see a rise in the device output. So this has kind of exactly the parameters that we want to have, and depending on the pulse parameters, you can change this integration time, also the decay time and everything. So these are quite versatile in that sense. And now the idea is, if we can have exactly the intermediate resistance states that we would like to have for training these devices for deep neural network or any in-memory computing tasks in general. And for the polymer ferroelectric, what we saw is that the morphology of the polymer actually plays a big role in controlling and also the pulse amplitude and pulse duration. So the fastest of the pulses, like 20 nanosecond pulses, have the chance of giving you better linearity. So ideal is to have almost a fully linear weight update in your device, but normally no practical device gives this ideal linear behavior. So the more we can get close to this value, it's better. And what we saw that in devices where you have more domain pinning sites, it's much easier to control the intermediate states. And with shorter pulses, you actually can have, let's say, very gradual domain rotation compared to a huge amount of rotation at the beginning and then eventual saturation, like exponential, that is normally observed from most of the devices. So what we understood that, okay, faster pulsing scheme and some engineered domain pinning sites could be the most ideal solution. And for any polycrystalline ferroelectric, the domain switching mechanism actually follows the nucleation limited switching properties. So very quickly going through it is, okay, depending on the applied voltage and pulse duration, you can actually figure out what pulsing scheme and what amount of programming voltage you really need to achieve a certain state, and you can figure out from the amount of domain switching and R on off where you want to have your device to operate. So, and also based on these fittings, you can find out the mean switching time, and which is kind of a Lorentzian distribution for a certain applied field. So these are all important parameters that we need to figure out when we are going for applying these devices for the network training. And for the ferroelectric field effect transistor, very quickly, this is still not fully published results, so I can go through quickly that, okay, when we have this MOS2 as the channel semiconductor and the ferroelectric as the top gate material, it's possible to have very sharp on-off switching, but in these cases, we really couldn't control the intermediate states very well. And what we found out that when we replace the ferroelectric layer by ferroelectric and dielectric both layer together, then it can show more like the on-off switching, but then at the same time the switching voltage also increases. So this can be modified with a thinner dielectric ferroelectric layer or multiple layer in stack, so that we can get the proper intermediate states and at the proper voltage value that we are looking for. Very briefly, we also worked on other oxide-based tunnel junctions as well, like strontium titanate-based, and at low temperatures, they can work very well and also have very stable intermediate states. They can work as cryogenic memories. So they have a lot of possibilities there, showing different kind of synaptic plasticity behavior. But yeah, I mean, I can come more to the next part than the adaptive sensor. And why it's important to have adaptive sensing is that, I mean, sensors are all around us now, doing all different kind of sensing, from health to like robotics and security and safety, autonomous vehicles and surveillance drones and everything. And what they are doing are, all of these are internet connected, and they are sending data all the time to the cloud servers, which is a huge loss of power and resource, because most of the time the data is not of any significance. So what is possible that if we can introduce local data processing and some local intelligence, so whenever there is an event of significance, only at that time the data will be communicated to cloud for further processing, or the data in case of, let's say, healthcare, when there is a situation of emergency, then only the data will be connected to the healthcare provider. So that is basically the idea. So event-based communication and local decision making. And in that case, the in-memory computing architecture next to the sensor could make real sense. So there are two different approaches that can be adopted. Like, one is close to the current architecture, that is the near sensor computing. So like here you have the sensor arrays, and close to that you have the processing unit. And this processing unit means it will take the raw image, do some noise suppression and some enhancement of the signal, and then it will take it to the in-memory computing circuit. So that can be applied for auditory sensors, image sensors, gas sensors, all different kind of problems. And then in this in-memory computing circuit, those filtered and enhanced signal will be processed using the in-memory computing circuit that we were discussing. And different kind of architecture is also considered for that, like the 3D monolithic integration or system on chip kind of integration, heterogeneous integration, chiplet kind of integration. So those are different options which can be done. So initially there will be data sensing, there will be low level processing, and then it will go to the neural network for doing feature extraction, classification, and all those tasks. And the second, and yeah, and in the other, okay, did I miss it somehow? Okay, no. So this is one of the things that we also studied with pressure sensing. So when there are sensors connected to the analog to digital conversion, and then connected to the neural network with memory state devices, you can really do different feature extraction and learning inside those pressure array matrix. So when you are writing something, putting pressure on those sensor pixels, and doing those learnings on the memory-based in-memory computing circuit, the system can actually remember those and can do the adaptive sensing part in that. But the next idea is doing everything in one single device. So it's the in-sensor computing part. So if we have, let's say, sensing and memory and control electronics all incorporated in one setup, it could be even more, better solution, because there will not be, too many components and circuits around. And currently we are working on some of the projects which are trying to do that. So one is European Union funded a project where we are studying multispectral image processing using this kind of architecture, where we have the sensing element and at the same time their cerebellar processor and cortex processor all will be integrated together, so that there is non-volatile memory keeping the image that is sensed, and then doing hyperdimensional computing with those data, so that there can be situational awareness and adaptive decision making done with that sensed data. That is one, and then one is an ongoing project also with NSF and Academy of Finland, where the idea is to develop a flexible sensor array integrated with the computing circuit, and also at the same time have it in a single device, so that each component, when it gets some external stimuli, change its conductance state, and that change of conductance state is directly in the in-memory computing circuit, so that it does the MAC operation already with the sensed data. And that could be the real solution for decreasing the number of circuit elements and also the latency quite a lot in that way. So the last part is, I have been talking so much about many different things, but basically the idea is we start from different materials. That is our main interest, like how device physics and material science can help you in getting very efficient neural networks, basically. But there are different steps and they are quite closely connected. So instead of trying to have extremely perfect material and extremely perfect devices, we have the option of playing around with a lot of parameters, so that we know, okay, what is good enough, and when we move to the next stage and don't get stuck with finding the best suitable material that we can achieve. So as I was telling you, let's say for in-memory computing, one key performance is the the states that is intermediate to on and off. So if we have that and we try to do some quick analysis, like when we have a device ready, we do some pulsed measurements so that we see how our conductance values are changing with continuous pulsing and with similar pulses. So we don't want dissimilar pulses, because that increases the circuit complexity quite a lot. And how those linearity we obtain from those devices, then the amount of change with each pulsing, like the delta G, and from one cycle to another, how that changes. So the cumulative probability of delta G, these are the parameters that are extracted from the device and from the experiment. And the next part is simulated in circuits and in the systems level, so that when you change the CMOS peripheral circuit parameters and the network depth and everything, then how your system would basically perform. And how that helps is that from device, we know exactly the material suitability, the interface functionality, the learning rate, weight update linearity factor, conductance range, maximum size of network, and performance in simple and complex tasks. All these things we can figure it out from that kind of a mixed performance benchmarking tool. And from the circuit, like the driving voltage requirement and pulse and time scale and quantization, and either the requirement of these analog to digital conversion circuits and noise injection or something like that. So just as one example, like when with our ferroelectric tunnel junctions, we did those training experiments for a deep neural network with the MNIST handwritten data set. So for large data set, you can see the non-linearity factor in weight update actually has a huge impact. Like the tantalum oxide memristors, which has quite noisy weight update, can give you only close to 70 or 75% accuracy, where the numerical accuracy is close to 98%, as the ferroelectric tunnel junction could give us something like 95%. And for smaller ones, actually, there was hardly any distinguishable effect on the training accuracy. So based on how complex task or how big network size we are going to have, of course, the device perfectness is quite important. So that is one thing. And currently we are working on this spiking neural networks based on the ferroelectric tunnel junction devices. What we see is that, using those neuron and synapse time constants, actually, because spiking networks also not only process the data on let's say space varying, but also space and time varying data sets. So that time varying part of the data comes actually from those time constants that we extract from the devices. So hopefully in future, I can tell you a bit more on how the device performs really on the spiking networks. That I come to the conclusion that innovative material and device design can lead to ultra low power intelligent devices, and materials to systems level benchmarking tool that we are working on. It can provide very fast hardware development, because otherwise hardware development is the most time consuming and the expensive part of the entire story. And integration of sensing and memory platforms could open a very vast era of smart and real-time operating devices, and that can have a lot of use cases, all in robotics, autonomous vehicles, healthcare, security and surveillance, and space and quantum error correction, and many other sectors that we can foresee. So thank you very much for your attention.
Thank you very much for this very inspiring talk. So questions? Yes, Giuseppe.
Hi. Why did you make such complex, the choice of such a complex substrate instead of using, I don't know, doped silicon? Because it would be just the technological transfer would be easier, no? Which is the difficulty?
I know. I mean, current research is actually based on having even low thermal budget semiconductors for it, because niobium doped STO.
Yeah.
I mean, it's possible. I mean, it's a very nice material to work with, because you can make actually a large change in, band bending also with the applied electric field. So in that sense, it gives very nice reproducible on-off switching ratio, but again, it's not really CMOS compatible. So low thermal budget semiconductor and changing the carrier concentration in those devices. That is one key target here. And yeah.
Okay, thank you.
Silicon is really one thing, but then when it comes to post CMOS integration, then polysilicon, but maybe with low thermal budget, where people have shown that with laser annealing or very short laser annealing, you can make those charge carrier concentrations possible. So post CMOS always have the thermal budget limit of 400 degrees or something. So it's very important in that sense to have low thermal budget semiconductors and with desired properties that you really want to have. So not only low thermal budget ferroelectric, as you know, HZO is now researched a huge amount, but low thermal budget semiconductor and the integration of low thermal budget semiconductor and ferroelectric and their interface, this is still not very much done. And for post CMOS integration, these are all very important.
Okay, further questions? Yes, Gustavo.
Hi, thanks for your presentation, Sayani. It was very impressive. I am very impressed in particular by the tunneling junctions because they need to be very thin, and ferroelectrics tend to be unstable when they are very thin, very unstable against depolarization and imprint. So the first question is, how thin were your ferroelectric layers? If you can disclose that.
It's and 5 nanometer.
Okay.
Mostly, yes.
All right, cool. And the second is pure ignorance on my part, but is there any asymmetry in the switching time when you go from the low resistance state to the high resistance state as compared to going from the high resistance state to the low resistance state?
It is. And also if we have this niobium doped STO as the semiconducting electrode, then definitely the creation of the Schottky barrier and the disruption of the Schottky barrier, their time scale is totally different. So you can see that asymmetry. You can try to control, it with a certain pulsing scheme maybe, because in all the training purpose, people normally look as much symmetric weight update possible, because otherwise all the circuit becomes very complicated to handle. So it's kind of possible to have tried, let's say, different pulsing scheme like pulse amplitude and width and duration and also interval between pulses. So those are the things that you can try to control so that you have more symmetric weight update. Both in case of potentiation and depression, but as these devices are not very symmetric, of course not. Yeah. And time scale.
I suppose it's inherent because part of the voltage will go as leakage in the low resistance state.
Yeah. So time scale wise, of course, yeah. There are things, and you really need to, for, let's say, deep neural network training, deep neural network is of course not the most energy efficient solution, but at the time it's the most developed networking system that people understand. And using the analog memories, you can actually accelerate the network training time quite a lot, although it's not the best solution yet. But deep neural network training requires you, let's say, plus minus 1 volt of maximum and pulses using the weight update linearity. So if you use 1 volt up and down, actually I didn't show here, but that paper is now currently under review. But it's actually, you have to figure out exactly at what point you could, using this plus 1 volt and minus 1 volt pulses, can have the best linearity that you want to have, because otherwise your training performance will be bad. And also another thing is, if you, let's say, in many papers, actually, it has been shown that, okay, you use 1.4 volt for potentiation and minus 1.5 volt or 1.6 volt for depression, that kind of training. But from circuit designers, I mean, they will be very mad at you if you say that I need very complicated circuits so that I can apply these two. So, I mean, it's quite a lot of things that you have to take into account when you are thinking from the device optimization side. Okay, I mean, we would definitely like to have those identical pulse programming, but yeah, always it might not be possible because of real physics challenges.
Okay, yeah, thank you.
Yeah.